So here are some of the highlights from the book notes that you had to complete, including all of the sample problems, which are probably the most important. But here you see, first of all, the main idea of gases that your book said. The fact that they can expand, diffuse, exert pressure, which we'll look at in more detail. And we can compress gases. You can force the particles to get really close together until even they become a liquid. The particles become so close together they actually attract each other and turn into a liquid. And it's hard to imagine, but around you right now there's tons of, billions of little particles, oxygen molecules, carbon dioxide molecules, atoms of the noble gases, and these particles are constantly moving in rapid random fashion. Now the first thing to look at is number 4 on your book notes, but the measure of the average kinetic energy of particles in a sample of matter is temperature. When particles are moving, they have kinetic energy, energy of motion, and we can detect that through temperature. And this is why we like to use the Kelvin scale for temperature, since 0 Kelvin is absolute zero. No more motion of particles, no kinetic energy to be detected. So as we'll see here, we're going to use the Kelvin temperature scale for all of our gas law calculations. Now pressure is probably the most important variable that we'll look at because most of the gas laws involve pressure, and pressure comes from particle collisions. That's number 7, the second part. When gas particles collide with each other or the container, they'll create pressure. And more particle collisions there are, the more pressure that's created. Doesn't matter what kind of particles. Carbon dioxide molecules, hydrogen molecules, helium atoms. Particles colliding will create that pressure. Temperature, volume, and amount of gas, which we like to call moles, we'll look at. They're also involved, but pressure is the main thing here right now. There are different ways to express pressure. Say that fast. One atmosphere of pressure, which we define as, atmospheric pressure at sea level on planet Earth, can be looked at through different ways. Kilopascals is the SI unit, so we'll see that a lot. There's 101.3 kilopascals is equal to 1 atmosphere. Millimeters of mercury, that comes from our very first barometers that weather people use to talk about atmospheric pressure. And that's how, at sea level, the mercury would rise 760 millimeters in the tube. PSI is probably the one that you'll see most often, pounds per square inch. And that, on your bike tires or your car tires, it'll give you a range of inflation in PSIs for the tires to operate the most efficiently. Now our first law we'll look at is Dalton's law of partial pressure. And it pretty much states that the total pressure of a mixture of gases is equal to the sum of the pressures of all the gases that are in the mixture. So here we have our first sample problem here, practice problem number 4 from page 409. What is the partial pressure of hydrogen gas if you've got a mixture of hydrogen and helium whose total pressure is 600 millimeters of mercury? And it tells us that 439 millimeters of mercury of the total is the pressure of helium. So simply put, the total pressure is the pressure of hydrogen plus the pressure of helium. We know the total pressure, we know the pressure of helium, so we just have to subtract, and that tells us the pressure that comes from hydrogen. Practice problem number 5 asks us to find the total pressure of a mixture. Well, how do you find the total of anything? You simply add it up. Thank you, Violent Femmes. So here we have these 4 gases that if you add up their partial pressures, it ends up being 13.78 kilopascals. The third practice problem, a little trickier than the first one because now we have to subtract out more than one gas. So if we want to find this partial pressure of carbon dioxide, well, the total pressure is 30.4, and then I have to subtract out the other partial pressures that are in that total in order to find the 10.2 kilopascals coming from carbon dioxide. All right, so that's our first gas law. It's not linked in with the traditional ones, but it is a gas law we'll work with. From chapter 13 here, the main idea for the gas laws is we see these four variables that we'll always be using with gases: pressure, temperature, volume, and the amount of gas, which again, us chemists love to talk about in moles. And essentially what these gas laws, we had some scientists working with gases and manipulating these variables. When you change the pressure of a gas, you're also going to affect the temperature and volume if you are holding the amount constant. And so the first person, Robert Boyle, that we're going to look at, we have Boyle's law, and it's stated as P1V1 equals P2V2. Well, P and V, pressure, volume, but what are those ones and twos? Well, the ones in our gas law equation mean the initial conditions, starting or original. The twos are after the change, the new conditions, the ending conditions. Most of these problems we're going to see are going to say, I've got a sample of gas at these conditions, something changes, so tell me about it. Or it'll say, here's a gas at these conditions, where did it come from? What were the original conditions? And so we're just going to have to be plugging in the right numbers in the right spot to solve these problems. So here's a visual of Boyle's law. All right, when I make the gas particles go into a smaller space, there's less room for them to play in, and so they will more often collide with each other in the container, so we'll have a high pressure. If I give those gas particles more room to play in, then they're going to collide less frequently. Less collisions, lower pressure. And so that's what Boyle was discussing. This also explains our breathing. Okay, so if you're going to go into the medical field or nursing or something, but your lungs have a certain volume. When you inhale, your lungs are expanded, the volume increases, there's a pressure differential, and air rushes in from the atmosphere to equalize that. When you're done and you exhale, the diaphragm contracts your lungs, decreasing the volume, and so the pressure is released by exhaling that extra air. So we have an indirect relationship. As the pressure goes up, the volume goes down, and vice versa. Volume goes up, pressure goes down. So here's our sample problem. The volume of a gas, 99 kilopascals, 300 milliliters. If we change that pressure up to 188, what's the new volume? So here's our equation. We need to plug and chug. Plugging the numbers in the right spot, 99 kilopascals is my initial pressure. The initial volume is 300 milliliters. The new pressure is 188, and the new volume is what I'm searching for. Numbers are plugged in. Now try to engage your brain though still, because, alright, if my pressure is increasing, my volume should be decreasing. So I'm expecting an answer lower than 300. So now I chug away. Multiply both sides, divide by 188, check my sig figs, and there's my answer, 158 milliliters, which makes sense. The pressure almost doubles from 99 to 188. So the volume is almost cut in half from 300 down to 158. Makes sense. Now, quick question. Since pressure and volume are involved in this equation, what about our other variables? Temperature and the amount of gas, moles. Well, as any good scientist knows, if you're looking at a relationship between variables, everything else has to be constant. So whatever gas laws we're working with, if the variables aren't in the equation, that means those other variables are being held constant. Alright, so the next two laws involve temperature, and again, as number 9 states in your notes packet, temperature must be expressed in kelvins, and that magic number to turn Celsius to Kelvin is 273. Whatever your Celsius temperature is, add 273, and that'll make it the Kelvin temperature. all gas law questions, you must have the temperature in kelvins. Some I'll give you in kelvins, some are in Celsius, so you have to change them. So first up is Charles's law. Charles's law, okay, we've got a gas at a certain temperature, and when you heat up this gas, the particles move faster, collide more often, collide with more force. So it causes the volume of the container to expand, assuming that we have the ability to expand, like a hot air balloon. You know, you're in the basket, the pilot heats up the air in the balloon expands until it is now less dense than the air around it, and the balloon takes off. If you need the balloon to come back down to Earth, then you cool the air inside the balloon. The air contracts, the volume of the balloon contracts, and now it becomes more dense, and you return back to Earth. So there's a little application of Charles's law. Here's our sample question. Now, my advice, as soon as you see a question that involves temperature, get rid of Celsius if you have to. Blah, 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 80 degrees Celsius, no. That's 353 Kelvin. 30 degrees Celsius, no. That's 303 Kelvin. Okay, I added the magic number of 273. That way you're guaranteed that you won't put a Celsius temperature by accident. So here we have an indirect relationship. Again, as the temperature goes up, this is a direct relationship. There's some noise behind me. As the temperature goes up, the volume of the gas expands. It goes up. Temperature down, we have contraction. So here's my direct relationship setup. And you're free to use that setup, but when you solve the problem, the first thing you have to do is cross multiply. So a lot of people prefer to set up the equation like that. And so here we're going to plug our numbers in. 3-liter sample of gas, that's my initial volume. The ending temperature is 303 Kelvin because the gas was cooled down. The new volume is what I'm looking for, and the starting temperature is 353. Engage your brain. Okay, temperature is decreasing, the balloon is contracting and coming back to Earth. So I'm expecting a volume less than 3 liters. And so when I chug away, multiply, divide, check my sig figs, 2.58 liters. The last law here involves pressure and temperature, the Gay-Lussac's law. And if you've ever seen a pressure cooker being used, essentially you heat up that pressure cooker that is sealed, and the temperature inside goes up way higher because of the pressure that's building up, and so things can cook a lot faster. Same thing here with tires. On a hot day, if a tire has too much gas in it, the temperature causes the pressure to build up, and you can have blowouts. Very common around here, especially in the spring with trucks. Here is my sample question. Again, get rid of the Celsius. 25, no, that's 298 Kelvin. 37, no, that's 310 Kelvin. Here's my law. Again, I cross-multiplied it out, so I just need to plug the numbers in. Here's my automobile tire. It's at an initial pressure of 1.88 atmospheres. The temperature goes up to 310. The new pressure is what I'm looking for. The starting temperature was 298. Use your brain. The temperature is going up. The pressure should go up. So I'm looking for an answer bigger than 1.88. Chug away, multiply, divide, check sig figs, and there you have it, 1.96 atmospheres. All right. Now this law also explains why aerosol cans say, don't put me in a fire, because if you've got a very flammable chemical inside an aerosol can and you throw it into the fire, that container is very rigid. The volume can't change, so the pressure builds and builds and builds until kabloom, and all of that flammable material meets the fire very quickly. So please don't try that. If you need to see that happen, that's what YouTube's for. Have a good one.